Good afternoon all. Today we are going to say about milk pasteurization. So the outline goes like this: the regulations and definitions of milk pasteurization and milk processing, that is nothing but a pasteurization, and effects of pasteurization and packaging and shelf life. So the introduction about milk pasteurization is why we do milk pasteurization is the first thing is to ensure the safety by killing pathogenic microorganisms and also to prolong the shelf life to destroy undesirable enzymes and to reduce the number of viable spoilage microorganisms. So these three are aims of milk pasteurization. And also our target is to achieve 99.99%, that is nothing but a 5 log reduction in viable organisms. So here the most heat resistant microorganism is Coxella burnetii. So we are going to do milk pasteurization for killing of this most heat resistant microorganism which is present in the milk. Actually this pasteurization is nothing but a mild heat treatment. This causes only minor changes in the milk flavor and nutritional quality. And also there are variety of milks. The milk means the whole milk, reduced fat milk, non-fat or skimmed milk which is free of cream, and milk beverages fortified. Nowadays there are supplements, vitamins, minerals and other nutraceutical components which are added into the milk to get a fortified milk. So that is they also called as milk. And organic milk, flavored milk, low lactose milk, so all comes under milk category only. So actually if we see the history of milk pasteurization, so we all know the word was coined after the name of Louis Pasteur, so who applied a heat treatment to increase the shelf life of the wine, right. So then he extended the same procedure to the milk to increase the shelf life. So initially when the pasteurization was done for the milk, so it was the heat resistant organism which is nothing but a Mycobacterium tuberculosis, so which causes tuberculosis. So in around 19th century, so that was around 19th century. So that time this was the Mycobacterium tuberculosis. So this was the most heat resistant bacterium at the time, so which causes the tuberculosis. To kill this pathogenic organism, first pasteurization was applied. So then after that they realized, so this is the most heat resistant microorganism which is nothing but a Coxella burnetii, so which causes a Q fever. Right, first country who made it mandatory for milk pasteurization was Chicago in US, and also after that the FDA, which is nothing but a Food and Drug Administration, so they made it mandatory for sale of interstate. If we want to sell milk between the states, then it is mandatory, the milk should be pasteurized first, right. This was done in around 1987. So this is the past history. Then after that there were many regulations and rules, there were ordinance, they were followed for the milk pasteurization. So we are going to see one by one. So the Code of Federal Regulations, that is CFR, so they defines the milk, what is called milk, right. So the lactal segregation practically free from colostrum. Colostrum is nothing but a first milk of any mammals after the newborn, obtained by the complete milking of one or more healthy cows. Milk that is in the final package form for beverage use shall have been pasteurized, so that is important criteria, or ultra pasteurized. So we will be seeing the conditions in subsequent slides. Shall contain not less than 8.25% of milk solids and non-fat, and not less than 3.25% of milk fat. Milk may have been adjusted by separating part of the milk fat therefrom, or by adding thereto cream. So you can remove or add, maybe some consumer wanted in that way, then the cream is added to the normal milk, or they may be separated from the milk as well. And concentrated milk, dry whole milk, skim milk, concentrated skim milk, non-fat dry milk. So all comes under the definition of milk, and milk also may be homogenized. So this is the definition Code of Federal Regulations gives for milk. Then the production of fluid milk in US is regulated by FDA, that is nothing but Food and Drug Administration. And also PMO, that is there are guidelines which are outlined by FDA, which is nothing but a pasteurized milk ordinance, and which specifies the pasteurization conditions and milk quality, antibiotic testing and current good manufacturing practices. So for all categories, so they lay down some ordinance, so which is called PMO, pasteurized milk ordinance, which was proposed by FDA. So those were guidelines. So according to that guidelines, what is pasteurization, which is laid down by PMO, which is nothing but a pasteurized milk ordinance. So the process of heating every particle of milk, this is very much important. So the moment I say okay, it should be 63 degree for 30 minutes, so each and every particle of the milk should be heated to that particular temperature and hold on to the particular time of 30 minutes. Our milk product is properly designed and operated equipment. For example, pasteurization. So what we do at home, right? We heat the milk. Is that pasteurization? So that is what. So it should be properly designed and operated equipment to one of the temperatures given in the following table. This we are going to see. So what are all the time temperature regulations for pasteurization, and holding continuously at or above that temperature for at least the corresponding specified time. So the particular temperature and particular minute, it should be heated to particular temperature and hold on for specified time at that particular temperature. So this following table we are going to see. So this is the definition of pasteurization according to pasteurized milk ordinance. And there is a international dairy federation as well. This is IDF, International Dairy Federation. So how they define pasteurization is a process applied to a product with the object of minimizing possible health hazards arising from pathogenic microorganisms associated with milk by heat treatment, which is consistent with the minimal chemical, physical and organoleptic changes in the product. So it is not only important to kill the pathogenic organisms which is present in the milk, and also it should not give any damage to the chemical or physical or organoleptic changes in the product. That is also important. So one such example is the alkaline phosphates enzyme, which is present in the raw milk, is slightly more heat resistant than the Coxella burnetii, which is the heat resistant non-spore forming pathogen, so which is present in the raw milk, right. So the heat treatment is applied to kill this pathogenic organisms, and also we need to take care of this alkaline phosphate. Sometimes the test is to conduct the phosphatase enzyme activity, whether if the activity is present, so that means the pasteurization is not enough, right. So we also have to reduce or inactivate alkaline phosphatase enzyme activity. But this regulation is given by US, right. So your pasteurization should be good enough to inactivate this alkaline phosphatase enzyme activity as well. But in European regulation says not only reduce the phosphatase activity, and also we need to take care of lactoperoxidase activity, because it should not inactivate this lactoperoxidase activity which is present in the milk. So they give minimum maximum ranges of pasteurization temperature. So what they say is pasteurized milk must exhibit both the phosphatase negative test, as I said, so this is also harmful, so we need to inactivate along with pathogenic organism, and lactoperoxidase positive test, because that is the enzyme which is present in the milk. Okay, so they give minimum and maximum activity, minimum and maximum. So it should show negative test for phosphatase activity and positive results for lactoperoxidase activity. Accordingly, the temperature is chosen. So in the subsequent chapters, we will also see how to choose a particular time temperature combination which kills the organisms as well as which does not give any denaturation of enzymes. That we will see in the subsequent lectures. Okay, so this is the following table what I was talking about here, given by PMO. So if it is a VAT pasteurization is nothing but a batch process. Okay, so VAT pasteurization is done for 63 degrees centigrade for 30 minutes. So this process is called low temperature and low time pasteurization, which is nothing but a LT. So here how it is being done is, first we need to heat it at 63 degrees centigrade and hold it for 30 minutes and cool it to the ambient temperature, then remove it from the batch by batch. So this is the energy consuming process, because what you do is you heat it to 63 and hold it, and we again to heat it you need to use heating medium, and to cool it to again to the temperature and you need to use cooling medium, and also you are taking long time. But process wise it is simple, because what you require is just one jacketed vessel to heat and hold and cool. But though I am saying one jacketed vessel is enough, but it is always a good practice. We already told it is a proper equipment, proper typical licensed VAT pasteurizer, you should do it. So then after that the continuous, that is nothing but high temperature short time pasteurization. So this is nothing but a continuous process. So this was introduced to reduce the energy consumption, which is a disadvantage in the batch process. So here the temperature is 72 degrees centigrade, the hold on time is 15 seconds. So here one advantage is, what happens is the pasteurized milk which comes out of the plate type heat exchanger. Here we use plate type heat exchanger. So the pasteurized milk which comes out of the holding tube is used to heat the raw milk, so that the pasteurized milk gets cooled and your raw milk is getting heated to some medium temperature. So that way you conserve some of the energy. So this is a good practice compared to the batch sterilization process. So the time consumption also very less compared to the batch process, it is 15 seconds. And also there are certain HHST process which is nothing but higher heat. So here high temperature short time, but here higher heat shorter time pasteurization. So this is done at 89 degree and 1 second, and 90 degree 0.5 second, and 94 degree 0.1 second, and 96 degree 0.05 second, and 100 degree 0.01 second. So these are all our HHST processes. And if you heat it to 137.8 degree for 2 seconds, so that is called ultra pasteurized milk. So in US most of the people prefer the ultra pasteurized milk compared to normal pasteurized milk, because this can stay up to 3 months, 3 months of refrigerated storage. So the temperature is a bit high, but sometimes the flavor, you get cooked flavor because of this high temperature. So this is the time temperature relation given for various process by PMO. So this is the typical continuous pasteurization. But there may be changes because sometimes we already discussed the milk means maybe whole milk, maybe organic milk, maybe skimmed milk. So, based on the product there may be changes in this diagram. So, it is like a generic diagram how the sterilization happens. So, the major equipment is this is a tank, right, and this is nothing but a pump. So, this is separator and this is a homogenizer, and this is plate type heat exchanger. So, this is holding tube. So, where it is holding to that particular temperature or higher. That is all. This is after packaging, this is process control and packaging section. So, in the plate type heat exchanger, so this is the regeneration section. So, this is cooling section. This is heating section. So, this is hot water, this is cold water. So, this is creamy milk, cream part. So, this is skimmed milk part. So, what happens is from the balance tank, the raw milk is pumped and sent to the regenerator section. So, where from here your pasteurized milk is coming. So, this is your pasteurized milk. So, it exchanges heat, then after that the raw milk is passed through the separator section via flow controller. So, this is nothing but one flow controller. So, these are all safety measures, these flow controllers and valves, certain valves are there and certain pumps also there. So, those were to check in between the conditions. So, then it goes to the separator where cream and skimmed milk part is separated. So, then this is the density transmitter, this is again flow transmitter, 7 is a flow transmitter. So, then 9 is another regulating valve. So, this 10 is nothing but a shut off valve. So, which if any problem then it will stop the input. So, then 7 is nothing but again flow transmitter. So, 11 is nothing but a check valve. So, it allows only this direction of the flow, and if you want cream then it will be taken from here, or otherwise it will go to the homogenizer. Homogenizer in the sense the large fat chunks will be homogenized into small particle size. Then if you want, then it can be again added back to the skimmed milk. Then 7 is nothing but a flow transmitter. Then it is pumped to the heating section of the plate type heat exchanger where hot water is used to exchange the heat. Then it is heated to the particular temperature. For example, we said it is 72 degrees centigrade at 15 seconds, right. So, in the hold on tube, so it will be almost the milk spends 15 seconds. So, which is now heated at 72 degrees centigrade at the heating section of the plate type heat exchanger. Then after that it goes to, this is FDV, flow diversion valve. So, what happens here is it ensures the 70 degree after it comes out of the holding tube, it is heated to 72 degree because it is held at 72 degree 15 second. So, if the temperature is not enough or it is not pasteurized to that temperature, then it sends back to the balance tank again, or if it meets the temperature regulation, then it has to go through the regenerator section. Then it goes to cooling section where cold water is used to cool and it comes. Then after that from here it goes to this section. So, further packaging. So, this is the generalized overview of pasteurization in the continuous process. So, there may be changes. I already told here, if we want cream milk, some consumer wanted the creamy layer above the milk. If the consumer wanted that product, or if the company manufactures that product, so then there is no need of separation. Or if they wanted to go for production of skimmed milk, then it is cream is separated, then only skimmed milk is going. So, this is the milk processing in US. Raw milk, so which is what we are having it in the balance tank, that is stored up to 72 hours, almost 3 days, at a refrigeration temperature legally below 7.2 degrees centigrade, but preferably at or below 4 degrees centigrade. So, in the balance tank you are allowed to keep it for 3 days, but if you are maintaining at refrigeration temperature. So, from the silos, raw milk is clarified, preheated, separated, standardized, homogenized, pasteurized and cooled. So, what we have seen is heating, pasteurized and cooled, and in between then some separation we have seen, right, the creamy layer from the skimmed milk. So, other than that, these also can be done. So, based on the industry needs, right, what for they have employed the pasteurization unit. And finally, the cooled pasteurized milk is pumped to the storage tank until packaged. So, here also we should ensure there is no recontamination issue. So, there are certain safety measures also taken while processing the milk via pasteurization. So, one is the flow diversion valve, as I said already. So, it automatically diverts milk back to the balance tank if the milk is not at the required temperature. So, if it is not at 72 degree, it will send back to the balance tank. And use of positive displacement pump, which ensures, so we use pumps to ensure that the pressure of the pasteurized milk is higher than that of the raw milk, so that there won't be any mixing at the regeneration section. Additional safety measures include an indicator thermometer, I already told while explaining the process itself, and positively sloped holding tube. So, for example, if I put holding tube this way, right, and there may be a chance of some milk packet stays here, right. So, when we put sloped, then it flows without any resistance, right. So, that way they ensure positive slope holding tube and vacuum break sometime, and placement of the balance tank below the inlet valve of the system. So, these are all ensures there should not be any recontamination. For example, if some milk packet stays in the holding tube, and also when the next batch of pasteurized milk comes, then there may be a temperature difference, right, with this milk chunk and what comes freshly. And also the milk may be cold separated before pasteurizing. So, what we have done, we have separated the skimmed milk with the creamy milk before pasteurizing itself to save the energy. And also energy can be saved if the cream flow is homogenized immediately following the separator and then added into the skim milk flow. Because the skim milk need not homogenize, because what we wanted is the fat part of the milk should be homogenized. In that way also we save some of the energy. Before that, as I told, in the safety measures, and also there is important thing when we talk about the batch process, the atmosphere above the milk, which is nothing but the head space, right. So, the head space should have at least greater than 3 degree temperature which is maintained in the milk. For example, batch process ensures 63 degree temperature at almost 30 minutes. So, your head space should be maintained at least 66 degrees centigrade to avoid any temperature difference, and also because it loses the heat, right, because the top layer is at 63, if your air layer is at normal temperature, there may be a del T. And also we need to ensure all the valves and inlet tube, outlet tube, everywhere there should not be any delta T in the sense if it has to be maintained at 63. So, all the equipment should also be at the same temperature, and if at all there is a del T, it should be less than 0.5 degree centigrade. So, literally there should not be any temperature difference. So, if at all, then only allowed is 0.5 degree centigrade only. So, these are all safety measures we need to ensure. It will greatly reduce your post contamination process. It is not only pasteurization, so there may be post contamination as well. So, then we are going to see one of the example for milk pasteurization. So, the problem is defined here. Raw whole milk at 7 degree is to be pasteurized at 72 degree centigrade in a plate heat exchanger at a rate of 5000 liter per hour, then cooled to 4.5 degree centigrade. So, the milk is pasteurized from 7 degree to 72 degree centigrade in a plate type heat exchanger. So, the volumetric flow rate is given here 5000 liter per hour, then it is cooled to 4.5 degree centigrade. The hot water is supplied at 7500 liter per hour at 85 degree centigrade, and chilled water has a temperature of 2 degree and leaves the heat exchanger at 4.5 degree centigrade. Chilled water in the cooling section temperature and leaving temperature is given. Each heat exchanger plate has an available area of 0.79 meter square. The overall heat transfer coefficients are calculated as 2890 watt per meter squared Kelvin. In the heating section, the same overall heat transfer coefficient is given for cooling section as well, which is 2750 watt per meter squared Kelvin and 2700 watt per meter squared Kelvin in the regeneration section. So, this is important thing, 75% of the heat exchange required to take place in the regeneration section. Calculate the number of plates required in each section, and properties are given, which is nothing but density of the milk is given, density of the water is given, which is at hot water because 85 degree centigrade. So, here it is, and the 1000 kg per meter cube at 2 degree, so which is nothing but chilled water. So, though the temperature difference is there in the heat exchanger, these properties are assumed to be constant throughout the range of temperature. The specific heat of water is given, that is 4.2 kilojoules per kg Kelvin, and specific heat of the milk is also given. So, our aim is to find out how many number of plates in the each section. So, we will write given data. One is milk side, another is hot water side, another is cold water side. So, milk volumetric flow rate is given, which is nothing but 5000 liter per hour. So, we would be using in terms of watts. So, we can better convert this into kg per second. So, for that you need to multiply with the density. Now, here we convert in terms of seconds, then later we will see meter cube per second we will convert, and later we will see. So, 5 because 1 liter is 10 to the power of minus 3 meter cube. So, 5 and 3600 seconds. So, which is coming around 1.39 into 10 to the power of minus 3. And the water side, it is given as 7500 liter per hour, same conversion goes here. So, 7 upon 3600, so which is nothing but 2.08 into 10 to the power of minus 3. So, this is in meter cube per second. Later we will convert to kg per second. So, in the cold water side nothing is given. So, then milk T in is given, which is nothing but 7 degree centigrade, and T out is given, which is nothing but 72 degree centigrade. And in the hot water side temperature is given 85 degree centigrade, and density of the milk is given, so which is nothing but 1030 kg per meter cube, and same way Cp is given, which is nothing but 3.9 kilojoules per kg Kelvin. And this side again density is given, which is 958 kg per meter cube, and Cp is given, which is 4.2 kilojoules per kg Kelvin. In the cold water side, so T in is given, which is nothing but 2 degree centigrade, and T out is given, which is nothing but 4.5 degree centigrade, and density is given, which is nothing but 1000 kg per meter cube, and Cp is given, which is 4.2 kilojoules per kg Kelvin. Right. So, this is all the properties we have written. And if we remember, we just have seen there are three major sections. One is heating, regeneration and cooling. In the regeneration section, the pasteurized milk which comes out of the holding tube is used to preheat the raw milk. So, that is nothing but a regeneration section. So, what are all the information given for all three sections, we will just see. This is heating section, another is cooling section. So, if we see, so all the section they have given a U. So, in regeneration section U is 2700 watt per meter squared Kelvin, and the heating section U is 2890 watt per meter squared Kelvin, and in the cooling section U is 2750 watt per meter squared Kelvin. And the important thing is, in the regeneration section almost 75% of the total Q is exchanged between the raw milk and the pasteurized milk. So, we are ready to calculate. What we supposed to calculate is number of plates in each section. Plates in all three sections. So, we will start with our regeneration section. So, regeneration section, it is told that 75% of the heat exchange is done. So, for that I need to know first what is Q. So, Q I will be calculating using MCP delta for the pasteurized milk. The mass is given, mass flow rate is not directly given, it is volumetric flow rate is given. So, 1.39 into 10 to the power of minus 3 into density is nothing but 1030, and the Cp is given 3.9 into 10 to the power of 3 because it is given in kilojoules, and the total temperature gradient is 72 minus 7. So, which is nothing but 65. So, this goes. So, the total Q what you would be getting is 3.6 into 10 to the power of 5 watt. So, in that 75% of this Q is nothing but 2.72 into 10 to the power of 5 watt. So, this much heat is being exchanged in the regeneration section. So, another one is the 75% of the temperature difference as well, because if you see Q is nothing but UA delta. So, U is constant throughout and area is also. So, then whatever the 75% of the heat exchange, we can also calculate the 75% of the delta across the regeneration section. So, which is nothing but the total delta is 65 into 0.75. So, which is nothing but 48.75 degree centigrade. So, this is delta which happens in the regeneration section. Now, we will be able to tell my raw milk enters at 7 degree and leaves at 7, plus we have calculated the delta is 48.75 degree centigrade. So, totally it is 55.75 degree centigrade. And the second one is pasteurized milk. Which comes out of the holding tube, which enters at 72 degree centigrade and leaves at again 72 minus 48.75. So, which is nothing but 23.25 degree centigrade. So, we know what is the delta across the exchanger now. So, delta across the regeneration section is, so this is 72, this is 55, so 72 minus 55.75 degree centigrade, so which is equivalent to 16.25 degree centigrade, 16.25. So, del T across the exchanger is 16.25 degree centigrade. So, we already know the formula, which is nothing but UA del T. So, what I supposed to calculate from here is A, which is nothing but Q upon U del T. So, we know what is the heat exchange, which is nothing but 75% of the total heat. So, which we calculated in the previous slide is 2.72 into 10 to the power of 5 upon U is given, U is given in the regeneration section. So, it is 2700 into del T we just calculated 16.25. So, which comes around 6.2 meter square. So, each plate area, this is the total area. So, number of plates is nothing but 6.2 and each plate area is given, I guess here somewhere, yeah, 0.79. So, 0.79, so which comes around approximately 8 plates. So, in the regeneration section, the number of plates required would be 8 plates. Okay. So, now we slowly move on to next one is heating section. In the heating section, what happens? The raw milk which heated from 7 to 55.75 will be introduced into heating section and it will be heated to final pasteurized temperature of 72 degree centigrade. So, the raw milk which comes out of the regeneration section at 55.75 degree centigrade is getting heated in the heating section and leaves at 72 degree centigrade. Right. Here if I want to calculate the area, so what formula I would be using is Q upon U del T. Del T, it is a logarithmic mean temperature, it is ln of del T. What is the clue about Q? Q we have already told 75% of the heat exchange is happening in the regeneration section. So, remaining 25% heat exchange happens in the heating section. So, I have a clue. So, I can calculate how much is 25% and U is given, but I supposed to calculate del T n, right, which is nothing but a logarithmic del T. But I know in the heating section raw milk enters at 55.75 and leaves at 72, but if you see the problem in the hot water side, you are given only the entering temperature, but I do not know what is the leaving temperature of the hot water in the heating section. So, I would be calculating here the del T of hot water. So, we know Q is equal to mCp del T. So, del T of the hot water is nothing but Q upon mass flow rate into Cp. So, Q I know, so 0.25 of my total Q is nothing but 3.6 into 10 to the power of 5. So, divided by hot water mass flow rate is given. So, which is nothing but we calculated 2.08 into 10 to the power of minus 3. So, this is nothing but a volumetric flow rate that has to be multiplied with the density, which is nothing but 958 into Cp. Cp is nothing but 4.2 into 10 to the power of 3, because it is given in the kilojoules, this will get cancelled. So, we are getting the del T of about 11 degree centigrade. So, I know del T of milk, the temperature difference which is happening in the heating section, and the temperature difference which is happening in the hot water side. So, then we will be able to calculate logarithmic del T, and Q already we have seen. So, this is nothing but 25% of the total Q. So, from there I will be able to calculate what is the area. So, hot water entering temperature is, hot water enters at 85 and leaves at 85 minus 11, because del T is 11. So, that is nothing but 74 degree centigrade. So, the del T for hot water side as well as raw milk side. So, the raw milk enters at 55.75 and it is heated to 72 degree centigrade, and we already told it is a counterflow plate heat exchanger. So, hot water enters at 85 and leaves at 74 degree centigrade. So, if we calculate del T logarithmic, so which is nothing but 74 minus 55.75 minus 85 minus 72 divided by ln of 74 minus 55.75 upon 85 minus 72. So, which is coming around 15.47 degree centigrade. So, we already know what is that. A is nothing but Q upon U del T ln. So, U already we told 0.25 into 3.6 into 10 to the power of 5, 25% of the total heat requirement. So, U is given for hot water 2890 watt per meter squared Kelvin, and the logarithmic mean temperature difference is 15.47. So, your area coming around 2 meters square. So, number of plates is nothing but 2 upon 0.79. So, which is coming around approximately 3 plates. Then there comes the cooling section. So, cooling section, the information given is pasteurized milk. So, pasteurized milk when it leaves the regeneration section, so if you see it is at 23.25 centigrade. So, it is cooled to 4.5 degree centigrade. So, pasteurized milk enters at 23.25 and leaves at 4.5 degree centigrade. So, the temperature difference we supposed to find out by logarithmic mean, and before that we also have to see because the A is nothing but Q upon U del T ln. So, in the cooling section we found out what is the entering and leaving temperature of pasteurized milk, but the entering and leaving temperature of the cold water is also given here. So, del Tm we know we can calculate, and we can calculate U, but I do not know how to calculate Q. So, that we supposed to calculate now. For example, if we see if we take the pasteurized milk, which is nothing but Q, Q is the milk is 1.39 into 10 to the power of minus 3 volumetric flow rate into density, that is 1030. So, into the Cp is 3.9. So, the temperature difference is nothing but 23.25 minus 4.5. So, which comes around 1.4 into 10 to the power of 5 watts. So, we know Q, then we supposed to calculate the logarithmic mean temperature difference. So, if we see in the cooling section, so one is the pasteurized milk enters at 23.25, which is cooled to 4.5. So, the same way my cooling water enters at 2 degree centigrade and leaves at 4.5 degree centigrade. So, del T ln, so 3.25 minus 4.5 minus 4.5 minus 2 ln of 23.25 minus 4.5 divided by 4.5 minus 2. So, the logarithmic mean temperature is coming around 8.06 degrees centigrade. So, area is nothing but Q upon U del T ln. So, just we calculated Q is 1.4 into 10 to the power of 5. So, divided by the U is given 2750 and the logarithmic mean temperature gradient is 8.06. So, if you substitute you will get around 4.7 meters squared. So, number of plates required is 4.7 upon 0.79, which is around 6 plates. So, number of plates in each section, regeneration section, around 8 plates, then heating around 3 plates, then cooling section around 6 plates. Okay, so this is the way heat exchanger, plate type heat exchanger is designed for pasteurization of milk in continuous process. And also here these values are approximate, approximately 4.7. So, for example, if you are taking more digits here, then you would be ending up with 7 or 8 plates. I might have done some numerical mistakes also. So, here the way how do you design is important. So, if there are any error, please excuse me while writing the numerical values. Okay, so then next we will see effect of pasteurization. Actually, pasteurization kills most of the microorganisms in milk, but does not render milk sterile. So, it should always be stored in the refrigerator condition, because the spores and thermodiuric bacteria may be especially difficult to destroy by that pasteurization temperature can be survived. So, the pasteurized milk must be kept under proper refrigeration temperature, preferably below 4 degree throughout the distribution and storage. And also this can be checked using standard plate count. So, the US regulation says the upper limit for the standard plate count after the pasteurization is the 20,000 CFU colonies per ml. Anyway, the fresh pasteurized milk will have less than that only. And also when you pasteurize, so what all happens to the, so this is based on microbial, right. So, we told that thermodiuric bacteria may be still there in the pasteurized milk. So, it has to be stored under refrigeration. The count is 20,000 CFU per ml if you do it in the standard plate count. And there are certain enzymes which are not affected, that is A and D, but B1, B6, B9, B12 and C all are having 10%, 1 to 5%, 3 to 5% and 1 to 10% and 5 to 20% loss would be there. And also this time temperature combinations during pasteurization. So, we have told, right, 63 degree, if it is a batch process 63 degree and 30 minutes, and if it is a continuous process it is nothing but 72 degree and 15 seconds. So, this time temperature combinations, it is no hard and fast rule that this time temperature combinations would leave this percentage loss. So, there is a quality consideration and optimization module of this course. So, that talks about how to optimize minimum destruction to the vitamins and maximum kill to the microorganisms. There we derive the best time temperature combinations to reduce this percentage loss. And there are some denaturation of whey proteins also happens during pasteurization, that is 3 to 5%. And most heat induced chemical reactions happens beyond 140 degrees, so we need not worry about much. And in enzymatic ways, and there are a denaturation of lipase and some proteases which limits the formation of off flavors in the pasteurized milk, which contributes to extend shelf life. And bacterial origin heat resistant lipase and some proteases cannot be inactivated at this pasteurization temperature. And also sometimes what happens, there is some enzymes called plasmin, which is the plasmin is increased by pasteurization, because the enzyme which transforms plasminogen to plasmin, so that inhibitor, right, so that inhibitor get inactivated during pasteurization. So because of which then there is a transformation of plasminogen into plasmin. So this also happens sometime, and you cannot do anything about certain heat resistant lipase and some proteases. So these are all effects of pasteurization on enzymes. And packaging wise, actually packaging should protect milk from microbial contamination and the intentional or unintentional addition of foreign objects. Right, there should not be any further contamination after pasteurization. So that is the basic characteristics of the packaging. And also you should block the passage of UV lights, right, or any visible light, so which can lead to oxidized flavors and also some loss of heat light sensitive vitamins. So your packaging should be high enough to block the passage of UV lights. And also it should be opportunity for communicating with the consumer. So the package should be attractive and all nutrition values should be printed on the packaging. So it should be printable, right? So that way also. So usually glass and polycarbonate bottles are preferred in the sense that is like they can be cleaned and reused, but the problem is while cleaning we should make sure that there is no recontamination. And also the glass bottles are very much unsafe to handle. We should take extra care to handle. So in that way this receives less attention when compared to plastic PET jars. So and there are some paperboard cotton milk cartons, but the problem is the opening, right, the opening and closing and resealing. So usually they are excellent light barriers, so which also satisfy our one of the three criteria, this criteria. But the problem is resealable caps. So once you are opening, then you may be suffering, I mean to reclose that opened package. So in that way, but nowadays new cartons are also coming up with resealable caps. So that problem is well taken care. And the most prominent one is the HDPE. So this is the choice of every dairy industry, and they also have separate molding section to produce HDPE based packaging. And also PET jars is gaining popularity because of single serve blow molded milk containers, because it is high clarity and consumer appeal, and also it has excellent oxygen and water vapor resistance. So this has oxygen and water vapor permeability is very much low. So that is because of that PET is the most wanted one. So to prevent light penetration, the plastic can be tinted with UV barriers. So there are some UV barriers or covers which is in film form, so that will be wrapped through the plastic can. So that also can be tried. And the shelf life wise, pasteurized milk can have a shelf life between 7 and 20 days or even longer. So this mainly influenced by the quality of the raw milk and post pasteurization contamination. So we already talked about this, is very much important, and especially at packaging and temperature control during storage and distribution. So these two places where post pasteurization contamination is very much happening. So we need to take care that as well. The shelf life is usually determined by microbial analysis or sensory analysis. So these two ways we do the post pasteurization contamination test. Usually the microbial tests are usually done after a certain storage time and temperature, and the result is correlated with the actual shelf life. So after that they do validation with the actual shelf life. There are two main techniques. One is the Moseley keeping quality test, which involves plating freshly processed milk and milk samples stored at freshly processed milk and milk samples stored at 7 degree for 5 to 7 days on a standard plate count. So, a large increase of microbial growth between first and second platings indicates limited shelf life. For example, I am taking processed milk and I am also taking milk which is stored at 7 degree for 5 to 7 days. So, then compare both, and if there is a microbial growth, then there must be some post contamination. And the Virginia Tech shelf life test uses a preliminary incubation of 21 degrees centigrade for 18 hours and followed by plating on standard plates or petri film and incubating for 24 to 48 hours at 21 degree respectively. So, then they compare both and validate how much is the contamination. And the main cause for the milk spoilage is this post pasteurization contamination, right? Because we told that there is a FDV valve which ensures the pasteurization temperature at the holding tube, right. So, only milk spoilage happens based on the post pasteurization only. So, that may be happening during storage or packaging or transportation, right. And post pasteurization contamination is the contamination of milk following the holding tube of the pasteurizer due to improperly cleaned and sanitized cooling sections, process lines, valves, tanks, fillers and packaging materials. We already told the care must be taken in the plant itself to ensure there should not be any temperature difference, but sometimes there may be improperly cleaned vessels or equipment and valves, fillers. So, that also the cause for post pasteurization beyond your storage or distribution or transportation or packaging. Actually, this contamination happens by psychotrophic bacteria, which are either Pseudomonas or Bacillus species is the most undesirable. This happens due to these two bacteria, but this is mostly undesirable. Actually, good process design and cleaning, good process design in the sense we ensure time temperature relation. To get time temperature relation, as we discussed yesterday, so all the factors to be taken into account, and cleaning and sanitation of both equipment and environment, and product temperature control from the point of the milk leaves the holding tube until consumption are also required to obtain a good shelf life, right. So, this is very much important. And also the coliform bacteria count. So, this will be done immediately it leaves the holding tube, because this coliform bacteria cannot survive in the pasteurization temperature. So, when the pasteurized milk out of the holding tube, so if we can do coliform bacteria count test, then that also ensures any post pasteurization contamination is happening or not. So, these are all some references and additional resources. So, you may would like to check for further milk pasteurization details. Thank you all. We will meet for next lecture.